Okay, so we're going to start with the definition of refraction. Below the refraction, you have a couple of images because so much of this stuff has to do with visuals, and visuals make it a lot easier to understand the wording. Okay, so I am going to stop my video so I can actually draw on this. All right. Here. Okay. So refraction is the bending of a wave as it enters a new medium at an angle with the normal line. Okay, sorry, I was trying to make, I'm like, I know there are like underlined spaces there and it might get a little bit weird, but that's okay. Let me make this thicker. So the idea is, in this illustration, there's our barrier, yes? Okay. The normal line would be a line perpendicular to the barrier. This like this thick. Does that make sense? Okay. The light coming in here is coming in horizontally. And then you see how it is no longer moving horizontally? Yes, as it goes into the new medium. So we've got a fast medium into a slow medium. It literally changes the direction. Here's our angle. Here's this angle. People, I believe you're still there. Okay. Now, if you take a look at the glass of water with the lines, do you see how the lines are going straight? Behind the water glass, do you see how all of a sudden it looks like the blinds are going at a crazy angle now?
Yeah.
That's refraction between the glass, the air, the light coming into the air, and then into the glass. And then you notice that when it enters the water, they're literally bending the other way because they bent going into the glass and then they bend again going into the water. And then everything looks incredibly different. Plus there's curves. This one's complicated, but you're seeing a lot of changes of direction. Question.
Wait, so the dashed green line is the light?
The dashed green line is the normal, the light is the red.
Okay.
Does that help? Okay, the light is red because that's where the little arrows are coming from. Light we're going to represent as a ray, which is like a line with the arrow on it. The green dash is the normal line. Okay. All right. Now, that's all well and good in illustration. Let me stop my share and let me start my video, make this huge, and I need to pin myself. Pin. Okay. Now we need to turn off some lights. I'm so sorry that it's still going to be pretty bright in here. And this is actually, to me, incredibly challenging because I like this, in order to do this well, we really want this to be a dark room. And those of you who are on Zoom are looking at that, you can attest. it's not exactly dark. Agreed? Do you guys agree? Yeah, this does not look dark. Okay. Totally ordering blackout curtains. I didn't do this unit last year here. I was doing it at home in my basement. I can make my basement really dark. But can't make this really dark. So, can everyone see the laser lines? Okay. Those of you who are in the room can also see that the lasers are continuing until we reach the wood. You guys see it on the wood cabinet? Okay. I need to stop doing that because I'm totally going to screw this up. Okay. Now, there's 5 on here. I really prefer if we could get it down to 1. So let me add some tape to cover these. Come on. Don't shine lasers in your eye. Oh, that's still 2. They've gotten stop shooting it into your eye. Okay. We can see that there's a single one now.
Yeah.
All right. So what property of waves did we talk about yesterday? It was another R property. Reflection. Okay. What I have here is a mirror on a block. Okay. If I put the mirror so that the laser light hits it perfectly horizontally, do you see the light reflects it? Well, you can see that it's reflecting off, or at least that it's stopping. Alternatively, if I angle this, can you see that we've got light coming in here and bouncing off here? Let's see if I can get this a little bit brighter. There we go. You can see it better now. Yes? Okay. And if we change the angle it comes in at, we change the angle it reflects at. Okay. Now, instead of having a mirror, I'm going to have a piece of plexiglass that has no mirror, completely clear. Yes, you can see through. My finger behind it. Yes, we're seeing that. Okay. And if I put it perfectly so that the laser is hitting it along the normal or at a 90-degree angle with the barrier, it goes straight through, yes? Look what happens when it is coming in at an angle. Can you guys see that it's not going and then it changes paths again? But these 2 paths are what? Louder? Parallel, absolutely. Trying to make sure that it gets recorded onto the Zoom. Okay. So these are going to be parallel, which we're totally seeing. Emily and Alice, how are we doing at home?
Good.
Cool, thank you. I love those reactions because I can get a quick visual that it's going good. All right. So we have that. Now, if we change the angle, okay. Are you seeing though that there's still some reflection here? Okay. At every barrier, there's going to be a combination of the reflection staying in the original medium. This is really hard to see on the screen, I feel like. You know, like if you're looking at over here, it's really hard to see this part. But there is actually, you can see the light hitting my thumbnail better. There we go. Okay. And if we bend it enough, do you see that, like here, we basically get the light being trapped inside, but it bends so much it gets stuck. This is what literally gives diamonds their sparkly lookingness, and cubic zirconia even sparklier. Y'all know that like stage diamonds are cubic zirconia? Because cubic zirconia looks more like diamonds than actual diamonds. It sparkles better. It just does. So it's really hilarious. I remember like Dateline or something before it became all true crime. Did a thing one time when they went down to in the Diamond District in New York, and they went down on the subway with identical settings. So like $1,000 setting, which basically means a ring that had a really nice ring with and everything, and had exactly the same size and the same flawlessness of the stones. One was diamond, one was cubic zirconia. So one was really expensive, one was just the cost of the setting, basically. And 85% of the people picked the cubic zirconia because it looked more like a diamond. Because it sparkles better.
It looks more like a diamond than the actual diamond.
Yeah, well, what it is they're like, there's all this life and bright color to it. But that's actually because, what?
Oh, no, she's showing me.
Oh, yeah, like how, nice. Actually, could you mind sending me that one?
Okay.
Cool, thanks. I love when students find things. So I will add this to the things that are up on our class page so you can see it for those people who are not here. But the idea is this refraction, this bending of light is something we can totally take advantage of. It also is something where we get those optical illusions. Have you ever seen, like, have you ever looked in your glass when you like put a straw in it and the straw is like split?
Yeah.
And it splits more or less depending on what angle you're looking at. That's the result of like bending so much, it's actually getting trapped inside. So what you're actually seeing is a reflection instead of a refraction. Or why, if you ever go to pick up coins in a fountain or something like that, or in the pool, and you go to reach in, and it's totally not where it, first of all, it's deeper than it looks, and it's totally not where it appears to be. You have to move your hand around a little bit. That's because the light is refracting or bending a little bit as it's exiting the water and traveling to your eye. Okay, so we're going to do more with this when we get to optical devices, but we need to do a little bit of mathy math. Okay. This mathy math is awesome. All right. We need to go back to sharing. Share my screen. All right, cool. We're back to where we need to be. Okay. So you have this image in front of you, hopefully, or we're able to look at this, that has the, they call this angle 1 is the angle of incidence. Remember, angle 1, we can call this theta r, is the angle of reflection as well. Okay. This is 1. And the law of reflection, which is my favoriteest thing ever because it's so easy, theta I equals theta r. Right, and that's lowercase r. We're going to change and call this angle 2 here the angle of refraction, which is going to be a capital R. Okay, so that's equal to angle 2. Now, the reason the light bends, the reason there is refraction is because you're moving between spaces that have different wave velocities. How fast does light travel in the air?
Yeah, that's right.
Yeah.
Yep.
Yeah.
The 3 sig figs of this 3 times 10 to the even for air. But if you notice it for 2 sig figs or for 1 sig fig, it definitely is. Notice I'm not doing it as 3.00 because there is a slight difference. But are you okay if I'm saying it's approximate?
Yeah.
Okay. The speed in water, okay. The velocity of light in water is definitely less than or slower than the velocity in air. Okay. Being able to determine what these values are is something that we're going to be talking about. And this is where the calculations start to get a little bit more intense. Is that cool? Okay. But here's the cool news. After today, there's still only 2 new equations for the rest of the year.
Nice.
Like once we get past today, and they cover 2 different topics. Like the next set of equations, when we get into the optics part, this is still like just properties of light and how light acts like a wave and what you can do with this. Once we get into applying that to optics, we only have 2 equations and it works for everything, and it's freaking amazing. I love it. Okay. Stop the video again so I can actually write. Oh, shoot. Sorry for those who are here. I just accidentally knocked the video feed to the projector out, so I apologize about that. So the equations we have to deal with today, the first one is index of refraction. Index of refraction is actually something that is the perfect thing to talk about on the day before the AP Chem exam.
Perfect.
Yay.
Because the index of refraction, if you are taking organic chemistry, which is not the AP Chem exam, but still it relates to chemistry. The index of refraction is one of the many ways and one of the easiest ways to help identify clear colorless liquids created in, and test the purity of these clear colorless liquids created in an organic chemistry lab. Is that okay? Like, yes. Name a clear colorless liquid for me. Anybody?
Water.
Water. What's another clear colorless liquid?
Vodka.
Vodka. Okay, and what's vodka made of?
Alcohol.
Alcohol. What kind of alcohol?
Oh,
Specifically ethanol.
yeah.
Drinking alcohol is ethanol. Has anyone here ever cleaned, like, has anyone here ever gotten a shot?
Yeah.
Oh, rubbing alcohol?
Rubbing alcohol or isopropyl alcohol. That's why I wanted to clarify. Vodka has ethyl alcohol in it. Vodka.
So don't drink. Don't
So
drink.
no, you should not drink rubbing alcohol. It is not the same alcohol and can be highly damaging to you. You can get very, very sick from it.
Yeah.
There's also an alcohol called methanol, which is something that people have drunk in the past when really, really desperate. Challenge of that is it makes you blind, literally.
Okay.
Oh.
Never
Methanol
mind.
poisoning can absolutely blind you. So don't take that.
You must be very desperate then.
Yes, yes, but it's also something like hand sanitizer, clear, colorless.
Yeah.
Okay, those are different. I'm just trying to be like, they're all clear and colorless. So there's a lot of different possibilities here. But what you want to do is you want to figure out what you made, and you want to figure out how well you made it, how pure it is. Okay, and that we can get by the index of refraction. The index of refraction is actually the ratio of light speed in a vacuum to the velocity of light in the medium. This can also be called the optical density. Something that is optically dense means light travels very slowly in it. The equation for this, is that N equals C over V. Okay, where N is the index of refraction. V is the velocity of light in that medium. And C is the speed of light in a vacuum. Now, indices of refractions are experimentally measured, but they're unique, kind of like a fingerprint, kind of like a density issue. You can have, if you have contaminants in it, you will get a value that's off by a little bit, okay? I was a complete and total moron in high school, or not high school, college on this thing. And I'm saying I'm a moron because I was taking organic chemistry. I'd taken this stuff in physics before. It never occurred to me that it was the exact same thing, that that's what I was actually doing. Like, this is that whole, you know, like how we refer to it as like you can't math and science because like that's a different topic. Yeah, like why would you expect me to do algebra in science class? That's like algebra is algebra class. Like, yeah, no. There's I'm like, they're intended to go together, okay? So I have pointed this out ever since I figured it out. Because I was like, oh my gosh, every organic chemistry lab I took, whenever we made clear colorless liquids, I'd go to this machine, I'd put a little sample in there and then like try to measure what it was and compare it to the actual value. And if it wasn't close enough, I knew I still had a bunch of water in there, so I had to heat it up some more and boil off more water. Like that's literally what was going on. But I want to point something out here. There's something you should know, something you should recognize. Remember how I said there's a situation where I would not accept I wouldn't accept answers based on like, you know how you okay yours, like you can use the wrong answer later. Remember there's a condition
If it's overseasonal.
or basically, if it's basically what I'm saying, what does the speed, if you have a velocity faster than the speed of light, what did I say you've done?
You broke the physics.
You broke physics. The issue is you can't break physics. Okay, this is another one of those you broke physics situations. Because, okay, what's the value? Okay. What values are the only possible valid values for n?
Less than 3 times 10 to the 8.
N?
It would be over 1.
Isn't it, if it's c divided by v, and v
Oh.
has to be
It can't
the
be over
speed of
what?
light or less,
1 or more.
it has to be 1 or more.
Wait. Oh, speed of light. Oh,
Yeah.
yeah. Other way.
Okay, n must be greater than or equal to 1. It's physically impossible. You broke physics if you get an n value less than 1. If you get an n value less than 1, I would suggest a couple of possibilities. Okay. The first of which is, are you in radians? Okay. You have to
Oh,
be in
usually
degrees.
is that.
You have to be in degrees.
You have to be in degrees. We're measuring our angles in degrees. You must be degrees. Okay. So these are the questions. The other possibility is that you didn't keep, like, did you keep remember how here we had like an air and a water situation? And we had an angle in the air and we have an angle in water? Did you keep the angle in water with the index of refraction of water? Did you keep the angle in the air with the index of refraction of the air? Like, did you keep the data paired? And we're going to do, and you're going to see that in a second when we do what is called Snell's law. Okay. Snell's law is actually how we measure the values of n. Okay. So this shows the relationship between the incident angle, which is theta I, and the refracted angle, which is theta capital R. Okay. And this is Ni sine theta I equals NR sine theta R. Okay. where Ni is the index of refraction. For the starting or incident material. And capital R is the index of refraction. Of the refracted material. I'm not gonna lie to you. I don't tend to use, I tend to get out of the I and R, and I tend to use like the terms for what the materials are. Theta I is the angle of incidence. And theta R is the angle of refraction. Okay. We need to do a little problem solving here. Are you guys cool? Have we copied everything? Are we good?
Wait.
Sorry. If, by the way, if you are using Word to take these notes, may I suggest you get familiar with insert equation. And you can type the equation and all the symbols are there and whatnot, which is super awesome. Now I've got to get back to where we were because, of course, life is life. Okay. Yeah, let's get to our, please have a calculator. Please have the calculator you intend to use readily available. Because I'm intentionally forcing you to do this calculation. This is one of those times, unlike when you're reviewing for an AP exam, that actually working through it is important because you need to know what your calculator is going to say in different situations. Cool. Basically, I'm going to attempt to break your calculator.
Okay.
Okay. I'm like, don't worry, it's not going to break. It's programmed to do this. That's fine. Do you want to borrow one? Okay. No, there aren't any calculators over there. Those are just data collection systems. I have. Yeah.
Okay, I'll show you.
Okay.
I didn't mean to show you for the longest time. But
No, I
keep
totally understand, but
forgetting
this
my own
is-
calculator.
This is one of those things I don't want anyone freaking out when they do this and when they do homework with this.
What?
Okay.
Oh no, don't use that one.
All right. So.
I know. Wait, can I use like a little tiny calculator?
Oh yeah, you can use any calculator. You can use any calculator.
No, I don't want to use
My child. Yeah.
Yeah, you want your 10 calculators, your 10 that's, I like just use, yeah, that'll work perfectly. But I just want to make sure you know what it's going to say. Okay. So. Yes. All right. Put a little more
These
light in
calculators
there.
are so expensive.
Really, I had to get this one in 7th grade, and then I had to get this one.
Yeah, the
Okay.
same.
All right, so light enters glass where n is 1.52 from air at point A with an incident angle of 45 degrees as shown in the diagram below. One of the things you will find is on our equation sheet, on the second page of the equation sheet, are a series of values for n, okay? I'm going to give you those now here so you don't have to look them up. But n for a vacuum is literally that's the definition of what exactly? So infinite numbers of sig figs with this. Okay, you can assume any of these have that, you know, this is not going to be your limiting, but for a vacuum, it's one exactly. N for air is 1.0004. Remember how I said it's approximately the velocity of light? That's because it's really close to 1. Okay. N for water is 1.33. And these are lists. You can find them in the handbook for chemistry and physics. You can in tables for materials. It's one of the properties, like they list the density and atomic or molecular mass, all of those types of things. They will list this as well. Okay. Now, we're starting here at A. Determine the angle of refraction at point A. Effectively, what we're asking for is this angle here. I'm going to label that theta RA. Is that cool by everybody? Okay. All right. We're crossing a barrier at A. Whenever we cross a barrier, we need to use Snell's law. Because Snell's law applies as you're crossing the barrier. Okay. So Snell's law states Ni sine theta I equals Nr sine theta R. Keep in mind, we're told it enters at an angle of 45 degrees. Because we know it's degrees, we know for darn tootin' sure, we have to use what units in our calculator? Degrees, yes. Can't be in radians, must be in degrees. Okay. That said, remember how I said I don't really like the I's and the R's because I think they're confusing? This is a me thing. This is an Ozism. Okay. I like to say, well, my incident material is air. So I kind of am like, N for air, angle in air. Okay. The material is moving into the refractive material is glass. So I need the N for glass and the angle in the glass. Does that help anybody? Do you see where that can be helpful? Because like, is it incident? Is it refracted? Who cares? What you care about is air with air, glass with glass. Okay. So N for air is 1.0. Do you guys want me to do it generically or numbers? Numbers? I heard a generic. Let me do it generically on this one. Okay. So this would be N for air times the sine of theta in the air divided by the sine of theta in glass. Oh wait, we're looking for theta in glass, aren't we? Sorry, divided by N for glass would equal the sine of the angle in the glass. Generically, we would then go to, how do you undo sine?
Inverse arc sine.
Arc sine or inverse sine, sine to the -1 of N air sine theta air over N of glass. Do we like this better than the I's and the R's? I don't know if you do. If you do, great. If you don't, that's totally fine too.
Anyway.
So theta would equal the inverse sine 1.0004 sine 45 over N for glass, which is what, 1.52 on this one? Yeah. Okay. Everyone typey this in your calculator, punchy punchy.
So it does have to be in degree setting, or like could you add like the degree?
Easiest thing to do is create a what I do is I create a document that's for physics that's in degrees and save it like that, and then I always use that document.
Okay.
You could add the degree sign in there every time, but you have to remember to add the degree sign to
Yeah.
each one.
No, but the question is, does it work if you're doing inverse sine? Because I'm not sure if that's.
I'm not sure about that either. That's why I just have it in degrees.
I don't think it works because I think it gave me my answer in radians.
No, I
Yeah.
just change it to degrees and then take it back.
Yeah, I'm like,
Oh, because I did it like this. That gives you the inverse sine, but I'm not sure how to do the inverse sine.
47.73.
very good.
Yeah, I didn't
Yeah,
get that.
Oh my gosh, you got that too. Oh my God. So
Wait, I said 7.353.
7353? Sorry. Yeah, we really only have two. Well, no, I think it's 45 in the diagram. It's 45.0. Sorry. And quite honestly, a reasonable number of sig figs. 3 sig figs is pretty much always reasonable.
Oh, yeah.
And then the.
Okay.
Have 160. Why?
All right.
You know what I mean?
Now,
Yeah,
determine the
maybe.
angle of incidence at point B. I'm going to do a quick re-sketch of this so that you can see it. This is so not to scale, like don't go measuring anything.
Oh.
Okay, are we good with that? Okay, here's my, sorry, this is a bad drawing, but that's okay. Okay, now,
Oh.
are we, question, are we crossing a barrier as we go from point A to point B? No, we stay in the glass, right? So what do we have to do if we're staying inside the glass? Do we use Snell's law?
No.
No. We need to use geometry.
Okay.
We can, okay. Keep in mind, we've got, this is perpendicular, this is perpendicular, this is a block, this is a square. So we can say that this angle here, yes, is congruent with this angle here, correct? We have two horizontal lines cut by a transverse line, opposite interior angles are congruent. So what is this angle? Isn't it 90 minus the angle we just got?
Yeah.
Okay. Maddie, what was that for me, please?
I was just thinking.
If you don't mind. Sorry.
62.2647.
Okay, sweet. I love that. Okay. So 62.3. All right. Determine the angle of refraction at point B. Okay, at point B, if we're talking angle of refraction, aren't we going to cross the barrier? So we need Snell's law. So we're going to be able to say N for glass, sine angle in the glass equals N for air, sine theta in the air. Okay. So we're looking for the angle in air. The angle in the air would therefore be, and I would assume you could do this in your head. And the sine theta in the glass is that 62.2647 question.
Well, why is it crossing the barrier?
It's asking this question, okay, sorry, this question now asks, I was just drawing the into the barrier here. It's asking, what is that angle?
Gotcha.
Does that help?
Yeah.
Okay. So this would be the inverse sine of 1.52 times the sine of 62.26, on and on and on, over 1.0004. Okay, I want everyone to punch this in their calculator right now.
Should it be the same?
You tell me.
I got undefined, did you?
Huh?
I got undefined. Unless I multiplied it wrong.
It's gonna be the same.
Oh. Yeah. Different. Yeah.
That's what you're talking about.
Remember how I said I'm gonna try to break your calculator?
Oh, right.
Okay. It's gonna come up as either undefined on a N-spire. What does it come up as on the calculator?
Error, math error.
Okay.
Me too.
How much do you want to bet that if the first time you saw this was on a test, the first time you punched it in and you saw error, you'd freak out?
Oh, very much so.
Oh, I do that all the time, yeah.
There's a reason for it. Okay, I'm erasing that for a second. Effectively, what's happening is, as it travels, now watch what happened. As we went from, okay, slow down, calm down, don't be mad at it. My computer is not working right now. It's frozen. I love this. Okay. If you can look at your whole paper. Oh, good. Yay. Okay, there we go. Now I can see this. Air, it started in something where air was very small, right? Small n, big R, or big theta, yes? Do you guys see that? Then you go from, and then here we're trying to go from big N, okay, and where the big N is, what happened to the angle as we went across A? If we have a small n and a big angle, we get a big N with a little angle, yes? Effectively, what's happening at B is it's trying to bend, and it wants to bend away from, so it needs to get an angle bigger than the 62.3 degrees or whatever it is, okay? So what happens is it gets to 90? Isn't that like skimming the surface? What happens if it tries to get to above 90? Is it actually leaving? No, it stays inside the new material. What do we call staying inside the new material or the original material? What? Refracting is going into the new material and changing direction. Reflection. It's basically getting trapped in the slower material. Okay, gets trapped, and we call this total internal reflection. We'll do total internal reflection. I'm actually going to make a short video on total internal reflection that I'm going to ask for you to do for homework. Is that cool? Does that work? Okay. In class right now, for the remainder of the period, I'm going to ask that you work on numbers 11, 12, 13, and 16. Okay. So I will make a short video. I'm actually going to make it right now.